thank you all for coming out today. It is 3:15 in beautiful San Francisco. We're at PyBay. The title of this talk is Unspeakably Evil Hacks in Service of Marginally Improved Syntax, Compile Time Metaprogramming in Python. You can follow along with the slides if you want at github.com/sanderson/PyBay2016, but there's going to be a fair amount of live coding in here, so I wouldn't necessarily recommend following along by yourself, but if you want to go look at the slides afterwards, that might be a useful thing to do. You can find me on Twitter at Sanderson, and there will be another slide with this stuff in a second anyway. So, cool. So, like I said, about me, my name is Scott Sanderson. I work at a startup in Boston called Quantopian that builds tools for anyone to do algorithmic trading in the browser and Python. Lots of cool things if you're interested in finance or numerical computing. They're paying for me to be here, so be nice to them. My background is in mathematics and philosophy. My Twitter is Scott B. Sanderson. My GitHub's Sanderson. Cool. And so a little bit about sort of the outline of this talk. We're going to start by kind of reviewing or introducing some what I'm going to call standard metaprogramming techniques in Python. Then we're going to talk a little bit about different ways that Python programs get represented either in memory or on disk. And then we're going to talk about a couple particular ways that you can muck with how Python interprets programs in various ways. So we'll talk about custom and file encodings, import hooks, bytecode rewriting, and then we'll end with sort of some philosophical, poetic conclusions about to what extent any of these things are reasonable or useful in the real world. Oh, and there'll be some spicy memes sprinkled in as we go. Cool, so metaprogramming. All great conference talks start with a definition from Wikipedia. So Wikipedia says, metaprogramming is the writing of computer programs with the ability to treat programs as their data. It means that a program could be designed to read, generate, analyze, or transform other programs, and even modify itself while running. So sort of stepping back for a little bit, all programs at some level are about performing transformations on data, right? You're in a web app, you maybe have data that represents users and transactions and shopping carts and cute things from Etsy and that sort of thing. But all programs are at some level about representing data. Metaprograms are the subset of those programs where the data is a representation of another program. And we can have lots of different kinds of representations of programs, right? We can have text, we can have abstract syntax trees, we can have instructions. There's all these different layers of abstraction at which we represent programs in memory as the data on which we compute. I think Exhibit would be sort of really into metaprogramming, right? You've got code, we're putting code in our code so we can write code while we write code. So sort of one of the very simplest forms of metaprogramming that we have in Python are decorators. So this is without decorators. So say we've got two functions here. We've got a noisy add function and a noisy save function. And noisy add takes two integers a and b, and it says, hey, add was called with these arguments, and it formats those in, and then it returns a plus b. And then we've got our noisy save function, which takes some piece of very important data, and it says, hey, save got called with this, and then it writes it to a very secure location. And when we call these things, right, we say, okay, add was called with args 1 and 2, save was called with important data, so that's great. But we might think, okay, well, we're basically doing the same thing in both of these functions, and neither of these functions is really morally about this sort of printing at the start of the function. So it would be nice if we could abstract out the noisiness of the functions into their own sort of separate piece of behavior and just have the functions deal with the very important business of adding and saving. And so we might write a decorator called noisy that we can apply to a function, and it says, I will print the arguments that were passed to f, and then I will call f. And so the way a decorator works generally in Python is you're going to write a function which takes some function f, and then makes a new function and returns that function to use in its place. So here what I'm saying is, okay, if you give me f, I'm going to write a new function called print and then call f, which is going to print and then call f. And then I can use that by sticking it on top of my functions with an @ symbol. And now I've got, oh, I didn't execute that last cell. Live coding. Right, and now I get the same behavior as my manual noisy functions, right? So this is a nice way for us to abstract out common behavior, and in particular to think about abstracting over modifications that we might want to make to a certain kind of function. So that's probably the most common source of metaprogramming that people get introduced to in Python. A sort of more advanced topic is what's called metaclasses. And metaclasses are tools that we use for controlling or transforming how classes get created. So one of the great things about Python is that it gives us all these really robust hooks into basically every sort of level of abstraction of our programs. And so we can do things like say, I want to customize what the class statement means or what it means to create a new type. So imagine, right, we're here, we've got this 2D vector class. So we're going to take an int x and an int y, and then we've got some methods on our class. So we can get the magnitude of our class, and we can make a new vector, which is the original vector doubled, which just multiplies both of the coordinates by 2. Right? And if I want to use one of these things, I'm going to say, okay, well, my vector is a vector of 1, 2, and then I can print the magnitude, which is v0.magnitude, open close paren. And if I want a doubled one, I'll do v0.doubled, open close paren, .magnitude, open close paren. So this is great. This is fine. This works for us. But we might think, well, these extra parentheses aren't really adding anything for us, right? These aren't really doing anything. There's no information that ever needs to be applied in order to take the magnitude of a vector or get a doubled version of a vector. So it would be nice if we could maybe simplify that syntax a little bit and not have to do that. And so one of the most common and one of the most known decorators in Python is property, right? So we can say, okay, instead of having a method, I'm going to wrap this thing into property, and then I can just use attribute access. Under the hood, attribute access will call my method. So that's great, right? We've taken away a little bit of boilerplate from this class, but now as library writers, right, we've had to duplicate and copy ourselves so much, right? We had to put property on 2 whole separate methods. And that's far too much work here, right? We're drowning in boilerplate in this class. So wouldn't it be nice if we could say, well, I actually want any method in my class that doesn't take any arguments to automatically get wrapped in a property. And so what we can do is write auto property meta here. So what we're going to do is say, all right, here's the signature that we want to automatically wrap in a property. So there's the inspect module, and the inspect module gives you all kinds of great tools for programmatically inspecting Python objects in runtime. And so one of the things that you can use to represent functions and function signatures in particular is this argspec class. So I'm going to say, okay, the argspec where my args is a single self, and I have no var args and no var keywords and no defaults and no quonly args and no quonly defaults and no annotations. And then what I'm going to do is write a new type that's going to replace the existing behavior for creating new types. And so what my meta class is going to get passed is itself, and then the 3 things that go into making a new type is the name of the new type, which is just a string, the bases of the type, which is a tuple of other types, and the class dict, which is all of the names that were in the body. So if we go back, oops, maybe. There we go. Right, so here there's 3 names in the sort of namespace for this class. There's a dunderInit function, there's a magnitude function, there's a doubled function. And so what we'd expect to get passed here is a dictionary mapping the string dunderInit to a function and the string dunderMagnitude to, in this case, a property object, and the string doubled to another property object. Right, so we're going to get past our name, our basis, our class dict, and then we're going to iterate through all the class dict. We're going to try to extract a signature out of that thing. If we can't, then we're going to assume it's not a method, so we don't want to wrap it in a property. And then if that signature matches our property signature, then we're going to print out that this is a property. We're going to auto propertyfy it, and then we're going to wrap it up in a property and put it back in the class dict. And then at the end, we're going to call super, which is ultimately going to call type.undernew and give us a new type. And so if we execute that, then now what I can do is say auto property vector, and look, no properties anymore. I just say meta class equals auto property meta, and now automagically my magnitude and doubled will get wrapped up in properties. So now magnitude is a property, doubled is a property, and so even though I don't have any parentheses, magnitude and doubled just automatically do stuff. Cool. So metaclasses, again, are a way of abstracting over what it means, what the class statement means, or what it means to create a new type. And there's some other sort of interesting, fancy things you can do with a metaclass, but at the core, it's really about this idea that I want to control what the class statement means. And then finally, as one other example of sort of standard metaprogramming, we have exec, which is sort of the Swiss Army knife of metaprogramming, right? Anything we can do with string manipulation, we can turn into code manipulation. And so say we wanted to be able to make like tuples that also had attributes as accesses. Who here has used the collections name tuple function at some point? Cool. So name tuple, all it is just tuples, but you can give names to the fields, and that's sometimes a little bit nicer. And we can actually implement a very simple version of name tuple using exec. And so what we're going to do is say, all right, we've got a template for a class, and it needs a name, whoops, and it's going to subclass from tuple, and then we're going to give it a under new, which defers to tuple, and it's going to need an arg list, and then we'll give it a repr and then some field definitions. And then all that simple name tuple here is going to do is take that class definition and template in a bunch of stuff based on a list of strings we got, and maybe there's a verbose and a rename and some other stuff. So it's going to build up a string, then it's going to exec it in an empty namespace, and then just grab the result out of that namespace and return it. And this is a little bit simplified, but this is actually how the real standard library name tuple is implemented. Name tuple under the hood builds up a big template, execs it, and then returns the value. The only extra stuff that name tuple does is there's a couple methods that don't really matter, and it does a lot of argument invalidation so that you can't pass it nonsense and get weird things coming out. And so we can do that in the same way. So I can say point equals my simple name tuple of x, y, and z, and p equals point of x equals 1, y equals 2, and then I can either use slicing syntax or attribute access syntax to get values out of this thing. So just sort of to review some sort of standard metaprogramming techniques, decorators allow us to naturally express modifications to existing classes and functions. Metaclasses allow us to customize class creation. And exec allows us to trade all of our awesome string manipulation tools up into program manipulation tools. And that can be very powerful for custom things. And it's not a tool that we should be reaching for all the time, but it is occasionally the right tool for the job. So great, right? Python is this wonderful metaprogramming land of rainbows and unicorns and sunshine. Why are we all here to learn about things that we don't normally use? So that's all great, but there are some costs to this. So some of these abstractions often incur runtime overhead. Right? In our decorator case, for example, we're going through 2 function calls now instead of 1. Certain operations can't be overloaded with standard tools, so there's nothing in standard Python or nothing in any of these tools that'll let you do things like customize what is means or customize what not means or change what it means to catch an exception. And there's no support whatsoever for syntactic extensions, right? So I can't abstract over the textual structure of my program and talk about, you know, maybe I want to be able to change what certain kinds of syntax mean or be able to add my own new syntax. There's not a lot of built-in support for these kinds of changes. And most importantly, it just doesn't really quite feel evil enough, right? We feel too good about ourselves and our souls writing this kind of code. So like Leo, right, in Inception, we need to go deeper. So let's look at we've warmed up a little bit. Let's look at a really complicated function now. So this is add2. And add2 is going to take a function, or take a value A, add 2 to it, return it. Add 2 of 1 is 3. So what actually happened when I hit enter there? So CPython took my code and sent it through several different representations of the program. So we started with the raw source code, which is just bytes. Then it used some encoding to interpret those bytes as Unicode. So we went from just sort of semantically, arbitrary small numbers to code points, which are actually some sort of textual representation. We then took that textual representation and converted it into an abstract syntax tree, which is sort of a Python-specific representation of the kinds of things that can be in a program. Then Python took that abstract syntax tree and said, I'm going to turn this into something that I know how to execute, which in at least CPython's case is bytecode. And bytecode are just sort of lists of, or instructions that represent what should I actually do when I execute this function. And finally, it took that bytecode and executed it. So just sort of as a quick overview of what all those steps look like, right? So I start with raw source, and if I can just look at, there's literally just integer values here, right? So this is a little bit easier for humans to read, but at the computer level, it's basically just seeing that I've got 100, 102, 101, 102, 32, et cetera, right? We just have bytes. So then at some point the computer decided, okay, well those bytes are actually Unicode code points, and so maybe it used something like the codex module to interpret them as UTF-8 code points and turn those into textual source. So now we have something that the computer actually recognizes as text. Then we took that text and used maybe something like the AST module to parse that into an abstract syntax tree. So that might look something like this. So I've got an expr whose value is a call, which is a function whose name is add_to, which has a context of load, and its arguments are the number 1, right, et cetera, et cetera, et cetera. So I've got these this tree of pieces that are now sort of at a Python semantic layer. And then finally, I'm going to take that syntax tree and compile it into bytecode. I have to give it a file name, and I'm telling it I'm compiling for exec rather than eval. And that's going to give me something like this. So this is using the disassembly module, which actually gives us the raw instructions that Python's going to execute. So you can see I'm doing a load const, a make function, a store name. So this is actually creating that function. And then down here, we can see the instructions in the function itself. So it does a load fast of the value a load const of the constant 2, a binary add, and a return value. And this is at the lowest level what the CPython virtual machine actually sees when it executes your code. So again, now we have to think to ourselves, all right, we've got all of these tools, we have all these different representations of our program. What can I muck with, right? There's all these different arrows here. Can I intercept any of these arrows and do interesting things with them? And the answer turns out to be yes for pretty much all of them. So let's talk about custom source encoding. So custom source encodings operate on the bytes to source text layer here. So CPython has this great feature that you can register your own encodings. And this is meant to be for things like other platforms where the default encoding isn't UTF-8. It's like UTF-16, or I want to be able to do other kinds of fancy things, right? I want to just be able to interpret bytes as different text. But there's no rule that says you can't use this for other things. So here I have a file that's rot13 encoded. And all that is just saying if I'm letter 1, which is A, then go to letter 14, or yeah, letter 14, 1 plus 3, et cetera. And then when I get to 13, wrap around and go the other way. So this is some mysterious encrypted text here. There's no way of knowing what this is, but it's been rot13'd. And you'll notice that I've said, hey, CPython, the encoding of this file is PyBay2016-rot13. And if I try to import that, Python says, I don't know what that is, right? PyBay2016, that's not a real encoding. There's nothing I can do with that. But if I go to the codex module and I say, codex, I want to register with you a new encoding, then I can register my search function, and now I can import that file, and we get hello rotated world. And just to sort of show you what that encoding file looks like, it's pretty simple. So you give it a search function that gets past the name of the encoding, and it has to return one of these codec info objects. And basically, this is just a struct with a name, an encode function, and a decode function. And there's some fancier functions you can give it for optimization purposes, but this is sort of a minimal complete definition of a textual encoding. So what is this actually useful for? Like, why would you ever want to do this? So there's a project from Dropbox, which is where, among other people, Guido van Rossum and Jessica McKellar work, called Pixel. And what Pixel lets you do is embed HTML in your Python program. So rather than just having regular Python, we can just put HTML elements in our program. So we've got this hello, and I'm going to say, all right, x equals the string hello world. And I'm going to return what looks an awful lot like syntactically invalid Python, right? I've got HTML, body, HTML. In regular Python, this would crash with some cryptic error about like less than not being in the right place, probably. But if I import Pixel, and what that does under the hood is automatically register the Pixel encoding for me, then now I can import that hello HTML function from my Pixel file. And if I call it, then I get an HTML object. So if I go back here, the return value that I'm returning here, even though it looks like literal HTML, is actually giving me an HTML object. And if I call stir on that, I can recover the original text that you'd sort of expect to get from there. And so this gives me a nice way of programmatically working with HTML and being able to interleave Python with HTML. So to sort of summarize how custom encodings work, encodings are registered globally with the codex module. They're opt-in on a per file basis. So you notice every file that wanted to use one of these custom encodings said, coding : rot13 or coding : pixel, right? So the file itself gets to choose this is how CPython should interpret me. Files that are using custom encodings still have to end in .py, so Python won't find them if they don't end in .py. We'll come back to that restriction in a second. And again, custom encodings sort of semantically operate on this bytes to text layer. All right, so that's all great. How about import hooks? So what happens when I do import blah from some file, right? So normally in Python, what that means is it goes and looks in your sys.path, and it goes and sees if I can find a file named whatever you tried to import .py, or maybe .dunderin if it's a directory, and then it reads that, interprets it with whatever encoding it has, and ultimately spits back out a .pyc. Right, so it's sort of it's handling the whole stack from some module name all the way to bytecode. But say I want to do something other than that. Like say I don't want a .py file. I want like a .hi file. So hi is another programming language. It's a Lisp. So you know, if you're familiar with Common Lisp or Clojure or Scheme or Emacs Lisp, say, you'd be sort of at home using this. And this is what a factorial function looks like in hi. So I'm saying, you know, def n factimple. If n is less than 1, then I just give you an accumulator. Anyway, it's not super important what this is, other than that there's a whole bunch of parentheses, and it's very clearly not Python, right? And so, again, if I want to import this, Python's going to say, what do you mean? There's no file named. So again, this file lived in /PyBay hiexample.hi. And if I just try to import that by itself, Python's going to be like, I don't know what a .hi file is. That doesn't, what does that mean, right? But, and so the place where I go to register, in the same way that we had the codex module with all these custom encodings, you can register new import hooks, which control what it means to import something. And so the place where those ultimately get registered is this sys.metapath list, and this is a list of module finders, which are basically responsible for taking the name that was requested for import and returning some object that actually knows how to take that string and give you a .pyc. And so what I'm going to do here is just print sys.metapath before and then after importing the hi module. And in case you haven't figured it out, hi is going to put something in sys.metapath so we know how to import hi files. So before I imported hi, the first element in sys.metapath was frozen import lib built-in importer. So this is probably just sort of part of reasonable CPython. And afterwards, I'm hi.importer.metaimporter. And so now if I go back to my example, and I compute a factorial, I can just do from PyBay .hi example import hi fact, right? So I've suddenly gained the ability to import from entirely different programming languages. And under the hood, that, you know, hi has its own compiler, its own sort of separate tool chain from CPython. Ultimately, it's taking my Lisp and recompiling it into a Python AST and then sending it to Python bytecode. So it has to at some point return to code that CPython understands, but in the interim, it can do whatever it wants. And so by registering my custom import hook, I gained the ability to point Python at files that it otherwise would have ignored or not considered as valid possible targets for imports. Another common example of this is Cython. So Cython is another language that ultimately compiles to something that Python understands, but in this case it's not bytecode, it's C. So Python's got a great C API, but C is a little bit verbose to write. Lots of people don't know C, and you can shoot yourself in the foot in all kinds of interesting ways if you're not familiar with C. And so what Cython lets us do is write in a language that mostly looks like and respects the semantics of Python, except we can give type annotations. So I'm going to say, all right, here's a Cython factorial, and my argument is of type integer, and I'm going to have some more integer arguments, and I'm just going to do for I in range 1, 10 plus 1, multiply my accumulator by I. And again, if I just tried to import that, it would fail, but I can. And Cython actually provides tools for generating sort of static C modules, but for interactive work, it's often nice to be able to import our Cython files the same way that we would import other Python. And so here I can say import pyx import.install, and now suddenly I have the ability to import from Cython files. And this is actually going to dynamically compile into C and then load it as a shared object. And so you'll notice here that my scifact function here is a built-in function or method, which is the type of Python functions that are actually written in C. And again, I get 120 as my factorial. And just sort of to give a sense of why this might be useful, I'm going to calculate factorial of 25 in both Cython and hi, which is essentially just Python. And we'll let those run for a second. So Python takes about 3 microseconds. Python takes about 50 nanoseconds, so that's what, 10, 20, it's about 600 times faster, am I right? 60 times faster. It's a lot faster, point being. So C is, in general, quite a bit faster than Python. Cool, so again, that's import hooks. To summarize, they're again registered globally here, right? We've got this one place sys.metapath where all of our imports have to live. And before I want to do some kind of fancy import, I have to register my import hook. In this case, the file no longer gets to choose how it gets imported. It's the loader that gets registered on sys.metapath here, right? So I can't necessarily, on a per file basis, say, here is how I should be interpreted. There's some other system that gets to decide how I should be interpreted. And unlike with custom encodings, there are no restrictions on file structure. In fact, we don't even have to correspond to a file system entry at all. So say that I wanted to be able to import from GitHub. I could do from github com.ssanderson import switch case. And I may or may not be still on the network. Yeah, we're not on the network. All right, we're going to skip that demo. Anyway. You can import from GitHub if you do one of these things. Cool. So those are great. Those are both interesting tools for the problems that they solve. One challenge with them is that both of them rely on some sort of external setup having happened beforehand, right? In order to use a Hi file or a Python file or one of these, or Pixel or one of these other custom encodings, someone ahead of time had to know that I wanted to do that and had to make sure that they set up that piece of global state. And so if you're, say, trying to distribute a library that wants to do one of these things, it can be tricky for you to ensure that your custom behavior has been set up correctly by your users. And so one thought we might have as well, we have bytecode, right? We have this very low level, very compatible representation of how Python understands code. What if we just rewrote that in place? And so that brings us to bytecode transformation, right? So we've got bytecode, right? We've got functions, they carry around the instructions of how to execute them. And we can just sort of loop here as much as we want and go from bytecode to new bytecode to new bytecode. Eventually we have to execute it or not. Not all programs have to get executed. But we can just sort of rewrite these as much as we want. So we're in CPython, everything's introspectable. We can actually look at what the fields of this thing are. So every function in Python, or at least every function that's written in Python as opposed to in C, carries around a $code attribute. And if I do add code dot, you can see there's all these attributes. I've got like an arg count, which is the number of arguments, co-consts, which are the constants that get used in that function. And probably the most interesting one is co-code, which is this terrifying looking just byte string. This is, again, just sort of opcodes that Python understands. And so if I call list on that thing, the actual instructions that CPython sees when it executes this are 124.00, 100.00, or 100.10, 2383. And we can, again, use the, anyway, so here's the full list of attributes here. So we've got co-code and const and file name and first line no and quonly arg count and lano tab and all these other things. And we can use the disassembly module to, again, show a sort of a human intelligible representation of these things. So here I'm just importing dis, and I'm saying dis.dis of that code. And now we can see that the raw bytes, 124.00, 101, et cetera, correspond to the following instructions. So we've got load fast, load const, binary add, and return value. So we've got our add to function. That's great. You know, addition's great. But addition is so 2015, right? And I've heard that all the hot new startups are doing multiplication now instead of addition. So let's say that I wanted to take my bytecode and replace all of the additions with multiplications. Well, looking back here, we can see that the first three instructions here are a load fast of 0, or the first 3 bytes. The second 3 bytes are a load const of 1, and then this 23 here is the binary add instruction, and that's the binary operator that Python's going to use to add the 2 values that I have. And so what if I just swapped that value out for the opcode for binary multiply, which I happen to know is 20? At least in the version of CPython that I'm on. These all change from version to version. So we can do this, right? I can write a function called replace all, which just replaces all the values in a list that match something with a new value. So, right, for element in the list, if it equals the thing I want to replace, then put in the new one, otherwise just use the old value. I'm going to grab the actual code of my add function. I'm going to call replace all on that and replace all the 23s with 20s. And then finally, I'm going to just print out my new disassembly. Right, so in my old disassembly, I had load fast, load const, binary add. Here I've got load fast, load const, binary multiply. And so unfortunately, or not actually, I can't just set new code on this function, right? Python won't let me do that. It says it's a read-only attribute. You can't just set new code on a function at runtime. But we can do is, code is a type just like any other type in Python. And the way you make a new instance of that type is you call its constructor. And the types module helpfully has all kinds of built-in types for us. So we can construct an instance of code type and just copy all the attributes that we don't care about from add and swap in the only attributes that we do care about, which are the new bytes, which are the old bytes with the one value replaced. And we'll give our function a new name just so it's not super confusing. And everything else we're just going to copy over. And now we've got a new code object that's basically like our old one, except using addition instead, or multiplication instead of addition. And then code object isn't actually what we want. We need a function object. We can do basically the same trick, right? And copy all the stuff that we're not interested in changing and just pass in the new values. So I'm going to pass in the new bytecode, but keep under globals and under defaults and under closure. Some of these actually are mutable, by the way. So you can do terrible, terrible things with that. If someone reminds me at the end of the talk, I can show you an example of one of the scarier things you can do in Python. Anyway, so at the end of all of this, I now have a mul2 function here. And if I call mul2 of 5, recall that nowhere in this did a function definition appear, right? We just started with add2, turned it into mul2. And now if I do mul2 of 5, I get 10. So I think that's pretty neat. Right, so we basically have ultimate power now, right? We're taking the lowest level representation of code that CPython knows about and just turning it into new things. So like truly the world is our oyster at this point. So, and we can start to see that there's kind of this pattern for bytecode transformations, right? So we want to start with some existing function. We want to extract its dunder code, apply some transformation to it, and then we want to create a new function by wrapping up all the stuff we changed and otherwise just copying everything from the old function. So we can do things like write interpolated strings. So anyway, so this is using a library that myself and a coworker wrote called Code Transformer, and it essentially lets you write these little code transformer classes. And the way they work is you match some pattern of instructions, and then you use that as a decorator on a generator that yields replacement instructions. So here what I'm saying is anytime I see a load const, if it's not a load const of a bytes, then just continue. Otherwise, what I'm going to do is essentially load instructions equivalent to the string.decode utf8.format ** locals, right? So I'm just going to grab all the local variables of my function and automatically format those into my bytes. And then I can just use that as a decorator, so I can do Ruby strings so for those who haven't worked with other dynamic languages, Ruby has this interpolation syntax. So in Ruby, just strings always work like this all the time. Stuff just gets interpolated in. So here I have some example function. It takes A, B, and C, and it just returns a string, right? It does not do anything with that string. But I'm decorated with Ruby strings, and some of these kind of look like maybe they could be an argument to format. And so if I call that, then it just automatically formats in my strings for me. And by the way, Python 3.6 actually has this feature for real. They're called f-strings. They look pretty neat. So more things we can do with this. We can do pattern matched exceptions. So how many people have at some point tried to catch an OS error and then been sad when they realized they had to do something with the errno attribute of that after the fact? All right, a couple people. Right, so unfortunately, up until recent versions of Python 3, basically anything that failed in the OS, you got one single OS error type, and then it had an attribute which was errno, which told you this is what the error actually was. And so if you were trying to be persnickety, you wanted to do something if a file wasn't there, but you didn't want to blow up if like there was a memory error or something like that. You had to catch OS error and then do a bunch of work in your exception, and that's kind of annoying. So it would be nice if we could just say, catch OS error of enoent or e again or e whatever else, right? There's all these sort of cryptic names for all these things. And so with Code Transformer, we can do that. So I can override what it means to catch an exception here. So I'm saying with pattern matched exceptions, I'm going to raise a value error of bar and accept value error of buzz, because we shouldn't hit this, right? That doesn't match. we'll return buzz, and then if there's a value error of bar, we'll return bar. Right, and again, if I tried to do this without doing anything fancy, Python would get very sad that I tried to catch an exception, right? It doesn't mean anything in normal Python to catch an instance of exception. You can only catch types. But with this, I can override what it means to catch an exception. And again, just sort of to give you a sense of what this looks like, the code here is doing the same kind of thing. So anytime I see a compare op, if it's a compare op of exception match, then I'm going to emit some instructions that do the right thing. So that's kind of cool. One more example is overloaded literals, right? So I can control what it means to have a literal data structure in my program. So here I'm just making a dictionary. It gets passed 2 values. And I'm going to return A maps to 1 and B maps to 2. And normally we'd expect to get a regular dictionary here. But again, we've decorated it with some sort of magic incantation. And now suddenly I get ordered dicts back here instead of an unordered dict. And again, newest version of Python, or no, sorry, that's only class bodies. More things will be overloaded dicts in the next version of CPython. So again, to sort of summarize, bytecode transformers, they don't require external setup, which is nice. They can be applied on a per function basis like any other decorator, right? So I can choose to very selectively control where this behavior is. You probably don't want ordered dict literals on every function in your program, but maybe in one function it would be nice. Downsides of this is truly relying on CPython implementation details. This doesn't make sense in PyPy or IronPython or Jython or anything like that. And it's relying, the bytecode is in no way a stable or public interface. There's no guarantees that it will change. It changes between minor versions. It changes whenever sort of somebody decides it would be nice. And probably most damningly, bugs will just segfault and do all kinds of horrible things to your program. So there's that. So sort of some conclusions here. Python's standard metaprogramming tools are pretty awesome, right? You know, I joked about the unicorns and rainbows, but in the scheme of things, we've got a lot of really powerful tools for, you know, controlling and manipulating runtime representations of programs. Import hooks and custom encodings allow us to extend syntax if we're willing to depend on global setup. And bytecode transformations give us isolated composable transformations at the cost of cross-platform compatibility and everyone yelling at you. So that's all of the material that I have planned here. You can see the talk content on my GitHub at sanderson.com/PyBay2016. You can find me on Twitter at Scott B. Sanderson, and you can find me on GitHub at ssanderson. And that's it. So thank you all for coming out, and I'd be happy to take any questions that you have. Yep.
So does this mean you can have like emoji variables?
I mean, you can have emoji variables in Python 3 already. Yeah. One thing I did actually learn about just the other day is there's the import Unicode data. So there's a module in the standard library that you can use to look up emojis as well. Oops. Look up. You can just get snowman or pile of poo, which is a real Unicode character. But yeah, as far as I know, you can just exec. Oh, invalid character in identifier. So maybe you can't. I could be wrong. You could certainly do that with a custom encoding. Yep. Yeah, totally.
How much people play with new features by starting to say, well, this is what it looks like when I hack it, and you can see how it works.
You're talking about like people who are working on, say, CPython itself? I don't know. I like, you know, my colleague and I, who we built Code Transformer with, we've mostly used it for toys and hacks and fun games. I think a real use case for it would be like quickly prototyping new language features that then you'd go back and do it in sort of a reasonable way after the fact. But I think more often they just sort of like cut a branch of the development repo and just sort of hack on it there. But yeah, if you wanted a lower cost way to doing it, something like this would be pretty reasonable. I mean, like I said, I sort of prototyped crappy F strings in, you know, a couple hours there. The real implementation of that's a little bit trickier because you have to recurse through constant values. But, you know, basically you can get 90% of the way there pretty quickly. Cool. Yes. Yes, this is, yeah, the tool that I'm doing all of this is a great extension to the Jupyter. So this is all actually just the Jupyter Notebook, which Carol is on the, I don't know what your official title is. You're on the board of something for them? Core developer for Jupyter. Yeah, so this is just the notebook. This is a great tool by Damien Avila, who's at Continuum Analytics, that lets you have sort of a live editable programmable slideshow out of it, which I think is pretty neat. So I wanted to show you guys the terrible mutable defaults. So say I've got a function def foo, and takes function or a value a and returns a. Right, so if I call that with no arguments, that barfs. If I do foo.dunderDefaults equals a colon 3. Oh, sorry. That needs to be just a tuple. That just works. That's terrifying to me. I only learned this fairly recently.